Hi, this course will be a simple course on probability for better understanding and a more intuitive approach towards understanding probability. Let's begin with first defining what's a sample space. So, in probability, we are understanding it based on a measure of belief, and it's a belief whether an outcome will occur or not. And so, we first define the set of all possible outcomes in an event, in an experiment, to be the sample space. And so this means that anything that can occur occurs within the sample space. And an event is basically a subset of the sample space. For example, you have 9 pebbles over here. The event that you choose pebbles labeled 1 to 5 is called event A. And then you choosing pebbles 5, 6, 8, 9 is event B. And so because it is a subset of the sample space, it is an event. So what is probability in this case? Well, we want to measure the chance or how likely it is for event A to occur and event B to occur. And we'll do so once we define what's probability. But before that, I would just say that we can do operations on events such as taking the union, the intersection, or the complement. So what is the complement of A? Well, that is 6, 7, 8, and 9. This portion over here. And having a union means now it means that to have this probability to occur is the chance of having A or B to occur. So it's the addition of these two. So the union is this event. Everything excluding 7. And the intersection will be 5. So I hope you understand now what is an event and what is a sample space. We'll take a look at more examples first so that we can have a better foundation before moving on. So more examples would include such as a sample space which is such as rolling a dice. Then the sample space is the outcomes 1, 2, 3, 4, 5, or 6. And the event is rolling maybe a 4. So it's one possible outcome of the sample space. Now, what is the probability that a dice rolls a 4? Well, intuitively, we will already think of it to be 1 out of 6 if it's a fair dice. And so, this comes with it, the naive definition of probability, where probability of an event occurring is just the number of outcomes divided by the total outcomes. And that of course makes intuitive sense because you want it to be the chance that something occurs. If let's say you have 2 possible chances to occur, then you divide it by the total number, then that will be how likely it is to occur. For example, the probability of having a tails is half because it's either heads or tails. And so if you, like I said, you can do operations on it. We can take the complement, which is just the heads. And that's really 1 minus half because now you have 2 events minus 1 over 2, which is half. But you can also think of it as 1 minus the original probability. And so while this is a good way of thinking about it, it really comes down to what happens if the total outcomes is infinite. Or the number of outcomes could be infinite. And it's like infinite over infinite. And so really what is a good definition to capture all these ideas? And that leads us to the definition of probability, where a probability is just a function such that it satisfies the following conditions. It sends the empty set to 0. it sends the sample space to 1, and it sends the union of mutually exclusive, which means that they are disjoint events and non-overlapping. You can just sum them up as each individual. So you can just think of it as heads or tails. They are mutually exclusive and disjoint, meaning they are non-overlapping. Means if you get a head, you cannot get a tails, and if you get a tails, you can't get a head. And so the probability of the union of these two equals the probability of heads plus the probability of tails, which equals to 1, of course, because it's the whole sample space. And with these two axioms, you are able to prove that the probability of any event will be between 0 and 1. And really, this captures our idea, because your chance of occurring can only be 1 if you have all the outcomes. If you have no outcomes, then it has to be 0. And if you are disjoint, then you can just add the probabilities up, because that's how likely it will be to occur now. Certain properties you can prove is that the complement is 1 minus the probability. If you have a subset, then the probability of this smaller set is always less than the probability of the larger set. And the probability of union for events that may not be mutually exclusive is probability of A plus probability of B minus away the intersection. And you can see this ties in with what happens if they are mutually exclusive. If they are mutually exclusive, then the probability of A intersect B is 0. And so, probability of A plus probability of B will be the remaining terms. And more generally, this is known as the principle of inclusion and exclusion, where you add all the individual, then you minus away the intersections, then you add back, like for example, then you add the sum of probability of E1, E2 and E3. So it's the intersection of 3 events, then you minus away the intersection of 4 events, and so on until you reach the end. And really, this hinges on the proof of part 3 of why it minus away the intersection. And you can see it from this picture, which is known as a Venn diagram. And it's a good way of representing the events, but it's not a formal proof. And by proving, you actually need to do the algebra manipulation. So this event, A and B, what is the probability of A union B? Well, it's the probability, if we take the whole of B first, then we only want A union A intersect B. So you want A intersect B complement plus B probability of B, because now these two are disjoint. And what's A intersect B complement? Well, it's this portion over here. And that's really the probability of A minus away the probability of A intersect B. And the reason for that is because the probability of A intersect B complement plus the probability of A intersect B must equal to the probability of A. And we shall show why in the future videos, but it's quite intuitive to understand this already. And really, if you want to read up, that's called the law of total probability. And so with this notion now, it gives us the understanding of when a sample space have equally likely outcomes, then each outcome is 1 over n probability of occurring, because the probability of the sample space equals to the sum of all these probabilities, and we know the probability of the sample space is 1. Since each event of occurring is the same, it is n times the event of 1 occurring, and so the event of 1 occurring is 1 over n. And this gives us the the probability of any event occurring is the total number of outcomes over the number of outcomes in the event over the total number of outcomes. And that is what our naive definition of probability says. Now, to strengthen our understanding, we have 2 examples for us to try out. So, let's say you have a community of 5 members. And in this selection, which is random, we want to know what's the probability that the community consists of 3 men and 2 women. Well, if you understand the combinatorics, which I've already gone through in a separate series, you can take a look there where it's more extensive. We like to say that the total number of ways is just 15, choose 5. Because there's 15 people in total and we need to choose 5 people. That's how you select a community. Now the number of outcomes for us to select with this condition will be the 6 choose 3 times 9 choose 2. And so, by what we have stated, if they have all equally likely, then it's taking the number of outcomes in the event divided by the total number of outcomes, which is 240 over 1001. I hope that's clear, and we shall move on. Now, let's take a look at an example to apply our inclusion and exclusion principle for probabilities. And that's really said that if you want to compute the probability that 10 married couples are seated randomly on a round table, such that no wife sits beside a husband, we can represent each event that a couple sits together as Ci. Then really, you want to take the union of Ci and its complement. So that the union of Ci will be all the couples sit together, and the complement will be none of them sit together. And so by the operation of the complement is 1 minus away the probability of this grand union. And this grand union can be equal to the sum of all the events minus away the sum of a 2 event intersection plus the sum of a 3 event intersection and all the way. And because they are all symmetric, all the same, you can just take 10 choose 1 times. So the event of one of the couple sitting together is 2 times 18 factorial over 19 factorial. You can review our combinatorics videos so that you can understand how I get all these results. But I'll explain for one of them. For example, let's say a couple sits together. Then there's 2 ways to arrange the couple times. Now there are 18 people plus the 1 slot of the couple, which is 19 slots in total. And the probability of arranging around a circle is 19 minus 1 factorial, which is 18 factorial. And the total number of ways is to arrange all these 20 people, which is just 19 factorial. And you can say the same for the rest if you follow the logic. And really, once you get that down and computing the answer is just pressing the calculator, and you get 0.3395. And so, this is really how we want to understand probability, is really the chance of something occurring. And you can use combinatoric analysis to help you when you have equally likely outcomes. We'll move on to a few harder topics in probability, but with this foundation, I hope you can follow up in the next video. This is the end of this video, and I'll catch you in the next one. Thank you for listening, and please feel free to like, share, and subscribe.